Welcome to today's Research Pays Off. I'm going to hand it over to our speakers for today, David White and Kera Gieselman.
Great. Good morning, everyone. Thanks, Lauren, for kicking us off. We're going to be talking about e-Compaction for pavement foundations this morning. Kara and I put this presentation together, and you'll see on the title slide, we're hoping to cover kind of the full spectrum of the application for this advanced technology. So it's impacting workflow on projects in terms of quantifying progress, making informed decisions, identifying problem areas with the foundation, evaluating performance specific to pavement design input values. And it's also a tool that's being used to communicate effectively and quickly. Oftentimes on projects, compaction, getting foundation materials is kind of the bottleneck to get to paving, which is sort of the main show. So having efficient communication through that process is important. I'll kick things off. Before we do that, I just wanted to give Kara a quick chance to introduce herself.
Yeah, thanks, Dave. Hello, everyone. My name is Kera Gieselman. I am the project manager for NGOs for our Iowa DOT projects. So happy to see you all today.
Great. Thanks, Kara. I guess to start off, some of the things that we'll touch on today, you might consider being different from current practice. And that's how advanced technology, is important in changing for the better how we do things. So a lot of what we'll talk about today is digital information, collection of a lot of data that's processed in the cloud quickly, and it's leading to these changes in workflow process. And we think this work is really important, particularly to help support the need to continue to push longevity of pavement systems to 50 or 60, 100 plus years. We know how important the foundation is going to be. E-Compaction involves geospatial presentation of data, and there's a variety of different types of information as shown on the screen here. There's material identification, pass count coverage, intelligent features that are built in to help with the inspection process. And ultimately, it's really to get to the point where we're able in real time to monitor results and reduce risk for the agency for making sure this is going to be a long life pavement system. A little bit about the technology. We referred to the equipment that goes on to compaction machines as CompScore RT kits. To make e-Compaction work, we're putting kits into rollers. There's a variety of different configurations of rollers, but for the most part today, we're just going to be talking about smooth drum vibratory rollers. That kit provides the ability for the operator to see the results in real time, and any remote viewer to see the same information in real time. One of the reasons that we're moving towards 100% coverage and geospatial mapping is simply because of point testing. The foundation materials tend to be the most variable of all the construction materials for a pavement project, but they're tested the least. And for the most part, since about mid-century, the approach hasn't changed. It's been spot testing on a limited basis. So this is going back about a decade now. There was an effort put out to look at spot testing. What are some of the advantages, limitations of that? And the outcome from that was, boy, if we could have reliable geotechnical data geospatially over the entire work area, that's a substantial change in how we can characterize and identify risk. I like to ask this question, and if we've talked before, you've heard me talk about this and reference this slide. What design value should we be selecting? If we trace the blue line across the screen here, and that represents the modulus of the completed pavement foundation, what number would you select as your input for pavement thickness design? And it's an interesting question because it's pretty challenging. If you know the blue line, that information, do you pick a really conservative value and have a thicker pavement? Do you pick something in between and just live with areas where we're probably going to have some type of cracking or fatigue issues in the future? What's the right decision? And ultimately, that's the bad question, because the better question is, how can we field control and verify that the design assumptions are achieved when the pavement foundation is constructed? One of the challenges is, although pavement thickness design has advanced significantly over the last 20 years with moving to more of a mechanistic approach, pavement foundation design has not. Largely, pavement foundations are specified and not designed. So the opportunity is, how can we close the gap between high quality pavement design and making sure that the foundation meets those design assumptions? And typically for the foundation, you've got one number, it's a modulus value, and that's what we need to be shooting for when we're building these things. So the idea is to just go ahead and measure that, control it in the field. So the concept: field verified pavement design inputs. For example, if it's a Portland cement concrete pavement, it could be K value. It could also be resilient modulus. And we're really focused on the top 3 feet of the foundation at this point, but some of the projects go much deeper, particularly around bridge approaches, box culverts, some of the structural fill for embankments. And then these are the positive outcomes: productivity, quality, improvements, and also training the workforce. We've enjoyed the opportunity to train about 100 operators on construction projects, and it makes the job more interesting. One of the things I wanted to make sure you left this meeting with was an understanding on how you could participate in these initiatives. These projects that we'll be talking about have been funded through a few different FHWA initiatives, mostly on the implementation side, not so much on the research side, but helping to get advanced technology into practice. One of the outcomes from the AID demonstration project with the Iowa DOT was creation of a roadmap. It's a 5-step roadmap that is pretty logical. Step 1 is assess where are you at as a state DOT. Does the construction office talk to the pavement design office? Do you have target values and methods of measurement to make sure pavement design assumptions are met? That's usually the starting point. And then that leads to getting out to the field, directly measuring the important parameters, participating in demonstration projects. And if you're thinking about getting involved, probably the easiest way would be to participate in a demonstration project, and there'll be a handful of those funded again in 2024. And then that leads to pilot projects, updating specifications, letting a few projects where this technology is used, and then finally implementation, getting to that improved practice. Kind of the main show of this, and you'll see several of these types of slides. This is an example of modulus that's output in real time as part of the e-Compaction reporting. This is K value. This one happens to be top of subgrade, and Kera will talk more about some of the specific details of these projects. And then this is the top of subbase. So quite a bit of improvement going from unstabilized subgrade to stabilized subgrade to getting the aggregate subbase down. And our design value is 150 PCI. So we're looking for this map to be completely blue. You'll see a few areas in red, and those are areas that we want to do some additional compaction to make sure that gets fixed before the pavement goes down. One of the great things about computers nowadays is they process a lot of data quickly. So important element of e-Compaction is that the data that's collected during that process is analyzed and made available to all of the users of this. So the contractor, the inspector, the resident construction engineering office, construction managers, pavement design office. So there's a back end that's built around this, allows that data to go from the field, from the machine to the cloud, translated into an e-Compaction report. And we'll check one of those out here in just a moment. And make all that happen in about 100 seconds so that essentially this becomes a real-time monitoring effort. Just kind of going back 1 second here, I just want to show a few pictures of the kit. So a kit is in the lower left. That gets set into the cab of the machine. All the rollers need to have a cab just to provide some security protection to the equipment. There's a monitor installed. This operator was just from a couple of weeks ago. She was trained up, took about 5 minutes. Here's the display. These are the things that you need to look for. There's an interactive touchscreen that's got buttons on it. And then the upper right is each of these kits has to go through a pretty rigorous check off so that the data is reliable. These kits are totally independent of the contractor and the roller manufacturer. They're essentially controlled by the state agency that's using them. So they're locked down so they can't be manipulated. Not that they would be, but just the perception. There's a clear separation there. So who has responsibility for that system? So that's installed. There's, for the most part, they're pretty quick to install. A hard install takes 4 to 6 hours, depending on the machine. Often the first hour is just cleaning the machine out. But they can be installed in the evening and then ready to go the next day. And then, as I mentioned, the operator is taught some of the features. They can go through a certification process that involves taking a 10-point quiz, sitting through a presentation, and then demonstrating over a 10-hour period of mapping that they're proficient at using the system the correct way. And if they do that, they can earn a certification. So recently, Minnesota DOT participated in one of the short-term demonstration projects. This is a design build project on 494. And we'll just jump over to the web application, and we'll let this load up here. So this is the report. It's this one's 22 pages. This is specified by the agency. What information do they want included? There's a few different ways of looking at geospatial data. There's a feature called blob identification. This is particularly important because it identifies the areas that need additional compaction. So you can see this one had 4 different segments, 1, 2, 3, and 4, that needed some additional compaction. And all the details for where those are located are automatically output. This one also had resilient modulus, both K-value and resilient modulus. So that was one of the features for this one. Pass coverage, elevation, lift thickness. This is a class 6 material. And part of this had a blob at the east end. So that area warranted development of a compaction curve. And what that shows is if you want to eliminate the poor conditions down here, how many passes would it take to achieve that modulus value? In this case, about 10 passes, 9 passes would be needed to achieve that. That's for K value, and then this is for resilient modulus. It's about the same number of passes. And then typically reports include a set of pictures that are uploaded. This is the compaction curve area on that project. So that's pretty much the gist of it. Get a map, use the map, figure out what action you need to take. If it's additional compaction, how many passes, and go forward to do that. Okay, let me get back out of that. Now, how do we get to modulus? That involves what's called calibration, and it depends on the pavement design. Is it AASHTO? Is it PCA? Is it ME design based? So the starting point is to really look at what was used from a design standpoint, and then go about testing in the field to verify those measurements with plate load testing. This is fully deterministic. So this isn't a black box. It is independent measurement, verification, calibration output, including how much error is associated with that. And we have some pretty high standards for what we would find acceptable so that this machine can be used as part of the quality verification process. So the rigor that goes into that is absolutely important for the agencies to have comfort in that output. Here's an example. More recently, we've started to get more involved working with the agencies on, okay, great, I see the map and I see that we've got some issues over here and over here. Now, how do we change our workflow? What exactly should we be doing in those areas? So we've been going back out more so the last 18 months or so, working on assessment in areas that are not meeting the pavement design requirements and doing additional compaction. And this one was kind of interesting because you see on the left, we had an opportunity to do a test and then did some additional compaction. In this case, it was just with a little vibratory plate compactor to see how stiffness would be changed for this granular subbase layer. It's an unoptimized layer, and we wanted to see how compaction would help that. And modulus went from 168 PCI up to 239 PCI 9 based on that plate load test. So that gives us good confirmation on site for those kinds of materials that if we want to improve that modulus, now's the time, get that additional compaction underway. Now, hopefully we've got a couple of videos that will illustrate this concept. There's a lot of different data features and software tools have been developed to help visualize the data. Here you can see an area that was identified where additional work was needed. This was interesting because the area that was improved there was recognized as a bad area. It needed improvement. So the improvement occurred in that area, but probably should have been extended a little bit. That's what the blob showed us. All right. In addition to outputting modulus from these maps, there's a way, and this is something I think pretty interesting, where we can use the data that we're collecting in the field and run that information back through the pavement design algorithm. And at every geospatial location, get a prediction for design life. If it's 0, that means we met the design life requirement. If it's green or blue, we achieved it. If it's yellow or red, we're not going to do that. And it really drives home the point that during construction, that's the best time to take care of these. So if we identify, look, this ramp area, it's going to be 5 years short of meeting the design requirement because of the support conditions of the foundation. Let's fix that. Let's get that to 0, or if we're really good, let's try to make it even better than that. So anyway, this map really is showing the design life before the pavement is put down. I'll show another quick video. This was an operator that was doing some mapping, had very little training. We said, hey, attack the red areas on the map, go back and forth. And, you know, it was very intuitive to the operator. You could see that action hopefully coming through, where there was a bad area and the operator immediately started going back and forth. You know, great. That's the kind of stuff that's typically missed with point tests. It's hard to find time to go to that location and get a test or have an inspector test at the location. But if we empower the contractor with the data and show them, hey, we're going to accept the results based on these map records, and here it is, it becomes a very efficient workflow for them to then build what you're designing around. At a national level, there is quite a bit of interest. As part of the AID project, there was a survey in 2001. There was about 30 states that responded to that, and overwhelmingly the states said, you know, in brief, we're advancing a lot of things, particularly on the pavement side, but we're looking for new things to do on the foundation. How do we advance foundation quality verification? And to a degree, there's kind of this lingering issue about foundation design that's going to have to be addressed. Again, foundation materials are typically specified, not necessarily designed on a project by project basis. And I think that's because there's generally a lack of tools that are widely accepted for foundation design. So at any rate, a lot of interest nationally to work on this. You know, part of the motivation for this, again, this 110 rule, 110-100 rule applies, where if we build the foundation right correctly, the unit cost is 1. If we don't build it correctly, and then we have to go back and do some rework, maybe it's ahead of the paver, maybe it's a different time, whatever, that's going to cost more. And then if we don't do it right, put the pavement down, and then that pavement doesn't last 100 years, the only way to fix the foundation typically is by removing the pavement. So it might be 100 or 1,000 or 10,000 times more expensive to fix that problem later than if we just take care of it right now. So we're looking at, you know, 40-year lifespan is fantastic, but if we're a little bit better on the foundation, can we position that foundation to support that pavement for 100 years or 100 plus years without having to go back and rework it? You know, good quality construction, taking care of the bad spots, you know, looking at different types of stabilization and how that's going to promote longevity. How do we factor that into the thickness design? Those are all things that are really relevant as the country moves and continues to move towards the desire to build these pavements to last much longer. So some of the things that we do at NGEOS, we're very focused on the advanced technology side of it, as we've been talking about, using plate load testing, setting up these machines for the agencies to map this data out. One of the pooled fund initiatives involves a technology transfer component. So we're getting things organized, these different case histories, and we'd love your participation as we launch the e-Compaction .com website to host all this information. So that's coming up. We'll be talking more about that at TRB this year. We've also had some workshops. Kera helped organize a national workshop through a pooled fund on this topic, had really good participation. And some of these projects have been featured as part of case histories where we're able to do full calibrations of plate load testing, get the machines set up, and then allow the contractors to operate those machines. Oops. If you're not familiar with modulus because you haven't been measuring it on your projects, these are some 100 cycle plate load tests on the right. That's about 25,000 PSI modulus, resilient modulus. And on the left, that's 100 cycles. That's about 3,000. So that kind of gives you a feel for the difference in modulus. So this is what we're measuring in the field. This is what we're setting up the machine to output. All right, we're going to talk now just about some results from projects. I'll mention a few, some recent work, also referring to MnROAD, and then Kara's going to talk about some of the details in Iowa. And then we should have some time for questions. One of the early projects where we were able to map out a lot of different foundation conditions was at MnROAD. And this was in 2017, and I won't go through all the details, but lots of different materials. It's a great facility for accelerated assessment of pavements and foundations, a lot of research projects around this. So we had the opportunity to map things out. And there's a variety of different cells, and each one's different. So we went through that process. And I think one of the things that was maybe the most eye-opening to the MnROAD staff from these results were these what are called jitter plots. It's a statistical presentation of every measurement point on a modulus scale. And all these different cells, again, had different foundations, different materials, different combinations of layers. And if you just look at this, you can see that some of those foundations are very uniform, even if the modulus is low. Okay, so that's good to know. Other sections were sort of normally distributed where we had values from low to high, just non-uniform conditions. Even though the average modulus might be higher, non-uniform conditions, which is something we don't want in the foundation. We'd like it to have good uniformity. And then some are not normally distributed. They're sort of have a concentration of values on one end, but exhibit a range on the other end. So anyway, that I think was kind of an eye opener that, we're building all these foundations, we're making assumptions from a thickness design standpoint, but the design equations for the pavement side don't capture spatial variability really in any way. So are the things that we should be doing to build these foundations differently so they're more uniform. And then we had a chance to go back. The first 2017 was on the low volume section. Then we went to the main line in 2022 and mapped out a variety of different materials. Again, lots of different sections. Some were milled surfaces, which was the first time we had a chance to do that. So that was pretty cool. Others was just standard class 5, class 5Q, aggregate sub-base, did a variety of tests, went through calibration. And we had a chance to map a shoulder section that I'm going to try to skip through this. It was kind of interesting because it had all kinds of materials. This is a area here that was not too great. Turned around, came back, went through all those sections again. And the results were really interesting. So of these sections had really low, poor conditions. And I talked to Raul and other folks out there, and they weren't surprised. This was sort of known that, in this stretch they had softer conditions. In other sections it was more improved. And I think it was good for them to see, okay, you've quantified this now. We can see what we sort of expected from the results. And there was a really clear delineation in these two cells here in that shoulder area. One area that was kind of bad, it stood out here. Was kind of interesting because we went back and looked at Google Earth, and sure enough, that section just in the shoulder itself had shown distress. They removed that, then we had a chance to come in and mapping. So that was a nice, just empirical correlation in that section. Again, jitter plots, looking at these different sections, different types of materials as we went through it. Anyway, a lot of different reports that came out of that. One that I thought was really interesting, it was something I learned. We had this blob show up. This was more on the eastern end. And the construction manager out there with MnROAD said, we've had some issues down here in the past. Go take a closer look at us and let us know what you think. And we went through a compaction curve process down there. And what was interesting is the modulus really didn't change as we compacted it. We went up to 16 passes. And this modulus value was correlated to the top 12 inches. That's the output. So the modulus in that top 12 inches really was not changing with additional compaction effort. But what was changing was the elevation. And you can see that in this picture. This whole profile was going down, but we weren't getting a modulus change in that upper 12 inches. So anyway, we talked more about that. And after the fact, the discussion was, it's not the upper section, it's what we've got deeper down. And I think what we're seeing here is that compactor was displacing some of that material deeper down. That's why we're getting that elevation change at the surface. So really interesting finding from my perspective that, if you don't get those materials deeper down, there's potential for permanent deformation to occur over time. And that's not captured very, very well in pavement thickness design. This is a construction thing that we've got to figure out how to address when we're building these, so that not only do they have the modulus that we need, but we don't want them to be suffering from permanent deformation over time. So that was a nice section for us to work on there. Recently, we've had a couple demo projects. I mentioned the 494 project, really complicated, interesting project in the Minneapolis area. We had a section to go out and do some mapping on a class 6 material. I mentioned that earlier. This is kind of what the profile looks like. Pretty good amount of variation in terms of modulus, from 500 PCI down to less than 100. There was a few blobs that showed up. We did some additional compaction in those areas, and I talked about that before. And then last week was Pennsylvania DOT. They do things differently on foundations, have this history of using kind of a lean concrete drainable base to pave on, and then underneath that is a sub-base material. And this particular project had cement stabilized subgrade. This is on SR 70, Interstate 70, south of Pittsburgh. Pretty good variation in stiffness. We were able to watch the whole construction process and see how placement of the material, moisture conditioning was affecting the stiffness results. On the edges, we had some soft conditions. So it was good to work with the operator and the contractor out there so that they can understand how to use that data during that process. Few blobs showed up, again, mostly at the edges, otherwise pretty good. And then this is going on actually today. It started last week. There's US 20 with Indiana DOT involves some mapping. It's kind of a granular structural fill, and then has some aggregate base layers. This is a really interesting research project, University of Illinois, Urbana-Champaign. Professor Tudemloer is leading to install some specialized sensors in the ground there. So look for some really interesting things to come out of that project. Overall, the structural embankment fill, not unlike a lot of materials, but fairly soft material. Really, the results here are a characteristic of the material type. We are working on some additional compaction to see how that can improve things right now. But this is going to be built up in different layers and include some geogrid stabilization. So what's happening here the next week or so are these additional layers will be built up. This was another section with blob analysis. This was a little bit bigger. Blob analysis, again, we want to take care of these blobs before the pavement goes down. All right, I'm going to kick this over to you, Kara, if you're ready to jump in and talk about the Iowa results.
You bet. Thanks, Dave. So Dave mentioned the Iowa DOT AID project, and I'll just give a little bit more background on that project. In 2019, the Iowa DOT was awarded an AID grant to implement improvements to their pavement foundation construction and testing process. The DOT partnered with NGOs to develop a demonstration program, which resulted in 13 different demonstration projects across the state in 2019 and 2020. NGOs technology was deployed to projects and utilized in addition to existing QC/QA project requirements to verify that the modulus values assumed in design were in fact being achieved during construction. Take note here of the last bullet point. A very important outcome of the demonstration projects was the finding that 70% of the measurements did not meet the assumed pavement design input values. Next slide. This is a graph of all the measurements. We know that we want our target K value to be 150 PSI per inch, or PCI, because that is where we begin to see less permanent deformation. And you can see here that only about a third of the measurements were actually above this. So this is a good example of why we need to be verifying that our design values are in fact being achieved during the pavement foundation construction. Next slide, please. Okay, so one of the objectives of the AID project was to develop an implementation plan, and the resulting plan developed by the Iowa DOT included a special provision, or SP, specification on 2 projects in 2021, and then increasing the number of projects over the course of 5 years with the eventual goal of a full statewide implementation of modulus verification using roller mapping. So we started in 2021 with 2 projects, increased to 4 projects in 2022. And then this year we have 6 projects for a total of 10 projects to date. 938 maps have been generated, and close to 30 million square feet have been mapped. The special provision modulus verification using roller mapping of pavement foundation layers is in addition to the existing QC/QA project requirements on these projects. The special provision requires the contractor to use their smooth drum vibratory roller outfitted with NGOs technology to map pavement foundation layers. E-Compaction reports are then used by the agency to make decisions on where additional effort or improvements need to be made on projects to achieve the assumed pavement design modulus values. In the next several slides, I'll show some examples of how the Iowa DOT is using the roller mapping in their decision making. This was a reconstruction project in 2021 on US 20 in Blackhawk County. The mapping on the left, top left, on the US 63 interchange loop B identified several blob areas. A blob area, as Dave talked about earlier, is defined as a contiguous area, and in this example, it was at least 1,000 square feet where the target modulus or K value here was not met. So the settings can be defined by the agency as far as the area and the target value. In this case, the DOT inspector required additional compaction to be complete, and then the resulting map in the center showed a decrease in the blob areas. The inspector then required additional moisture conditioning and additional compaction. And you can see on the third map, the elimination of all blobs, indicating all areas met the target K value. Next slide. This was on the same project in Blackhawk County on US 20. The plan specified the use of GeoGrid in areas where minimum K values were not being achieved through compaction. So the mapping here on the left identified this blob area, and then the image on the right shows the placement of the GeoGrid. Next slide. This is on Highway 17 in Boone County in 2022. The project included the grading of bridge berms for a new railroad bridge on Highway 17. Highway 17 on the map is the left to right road. You can see north is actually pointing to the right, so that's a north-south road. And then also the grading and paving of Robin Road, the side curved road there. The map shows the blob areas in color. So the red, green, yellow areas are actually the blob areas here. And those were where the minimum K value was not met. Now the project plans specified the use of cement stabilization on the subgrade for areas not meeting those target K values. So the DOT decided to stabilize all of Robin Road in this case, and then the north half there, or the right side of Highway 17. One interesting, if you can go back to that slide, one interesting item to note there was a borrow just to the right of that farm that you can see. And so everything to the left of there was actually being used as a haul road. So there was reasoning there for those K values being higher. Okay, next slide. It is currently underway and is a reconstruction project on US 75 in Plymouth County. In the photo on the left, you can see an existing box culvert, and then above that, the subgrade material, which had been excavated to a depth of about a foot above the box culvert, and then filled with select soil. Then you can see the first 6-inch lift of a granular special backfill material had been placed and compacted. The map in the middle here that you see then was generated at that point, and then you can see over the culvert area, the K values in that area are fairly low. So we've got 35 and 57 PSI per inch for K values. Now outside of the culvert area, you can see point S1 has a K value of 158 PSI per inch. So the contractor and the DOT inspector asked us to investigate the results of this map. And GEOS staff went out and conducted DCP tests, and you can see the results of those on the right. We see here that when you get below that 6 inches of granular material, points S2 and S3 that were over the culvert, the CBR values dropped significantly. So the contractor then did inform us that minimal compaction effort had been used on that subgrade material over the culvert, and those map results clearly showed this. Next slide. Right, this last example is a project also currently underway in Dubuque County on Highway 3. This is actually the third segment on this particular project. In previous years, mapping results have shown extremely low K values, and averaging 40 to 50 PCI. Therefore, the DOT had decided to cement stabilize 100% of the subgrade on this project. Now, the map here that you see was completed after cement stabilization. Typically, we see higher K values and a lower degree of variability. But in this map, we're actually seeing a high degree of variability and pretty low K values. So after further examination of the area, the DOT inspector required core out and replacement with a granular material in the areas you can see marked with the red stakes. And then you can also see the K values and the core out dimensions here for each of those points on the map. Next slide. And this slide is a video here, so Dave, play that video. This video is on that same Dubuque Highway 3 project. So this was before cement stabilization, and you can really see some pumping happening here. And if you look in the bottom right, the map shows an average K value of 45. So we're seeing a lot of red here on this map. Then the next map will show after cement stabilization. It's lagging just a little bit. There we go. We have an average K value there of 100. And then this is on top of the modified subbase, so before paving. And you can see a lot of blue then on that map with an average K value of 162. All right, so these are just a few examples of where the Iowa DOT is using modulus verification with roller mapping to drive decision making and improve their foundation construction. Right, we'll open it up to questions.
Hi, thank you very much, David and Kara. Great presentation. So yeah, we are now at the time of Q&A. So if anybody has a question, feel free to unmute yourself and turn on your camera and ask the question. Also, you can put it on the chat and I'll read it to you guys. So I think I see Kurt Turgeon hand is up. So Kurt, if you can please go ahead and ask your question.
Well, so as I understand it, you're under contract with the Iowa DOT to do this testing. How have the contractors reacted to, I don't know, I can imagine some of them saying, well, this is just some kind of weird voodoo and, take these guys and get them off of my project. It would be, are the contractors, I mean, you indicated, well, the inspector told them to do a better job over there, and then they did a better job over there. That's not the contractors we deal with.
Yeah.
Yeah.
I would say, no, we've never had a contractor say this is voodoo or sort of work in that fashion. I think generally speaking, I think the contractors are moving towards more digital solutions, more real-time monitoring. And as you know, intelligent compaction in the United States has been underway for about 2 decades. So most of them have been exposed to it in different ways. Unfortunately, a lot of their experience with it has been, well, this just doesn't work well. And that's when we have the opportunity to say, we understand that, and that's why we're doing things differently now. And that's why we're linking this to design. That's why we're doing calibration. That's why we're giving you access to the information that the inspector is going to be using for acceptance verification. And, then that gets going, and then you run into a situation where you don't have a passing map like Kara showed. And as Kara walked through, here's the things that actually happen on the project when that occurs. I think the thing about implementation of advanced technology is the specification has really got to be written so that the contractors had an opportunity to participate in what that looks like. if you move too quickly and shift too much risk to the contractor, that's when things start to get more challenging. It's not the technology itself. It's just making sure that the contractors, I think, understand what that risk looks like, how to bid the projects accordingly. That's my thought.
Yeah, I would, definitely agree with that. So I mean, you're costing the contractor time when they make them go back and rework and I guess I'm just curious how the specification says, if we tell you got to go redo it based on what NGO tells us, that's your fault, not ours. And the time factor of developing all this, I know we ran into problems years ago with, we have information that says you're doing a lousy job, and the contractor says, well, if you make me redo it, that's not in the contract. I'm going to file a claim for having to redo it.
Yeah. So, that's the risk of doing new things this way that show, hey, we've got a problem. So sometimes it does require more time, but the real question is it worth it? And the answer is yes, it's very much worth it, because the impact it has on the public and the cost later is exponential relative to that time it takes right now. The other thing is, we've got to be a little bit careful to hold the contractors accountable for materials that aren't adequate to achieve the design requirement. So it's not their fault that the specified pavement foundation materials really aren't very good materials, and that no matter how much compaction you put into them. So I think there's new understandings now that, hey, we're seeing things now in the field where we've got to go back and look at, are we designing this foundation? Do these materials have the potential to meet the design requirements? And if they do, then it's just a construction issue. Let's get these things built right. If they don't, well, let's work on the design side or have stabilization options, appropriate bid items to make it work.
No, I think it's great technology. And I'd love to see us being able to use it, but having been through this before with other stuff, it's like, man, it's a long road to go from the whiz bang stuff to the guys with dirt on their shoes going, yeah, what's the data telling me? Because I want to know now. That's a long way to go. Sounds like you're well on your way in Iowa, though. Thanks.
And I'll just add, thanks for your question. And I'll just add that in the field, speaking to the project foreman, the overwhelming response from them is this is great, and we want to use this, and why aren't we using this across? They're really enjoying seeing this data, and they want to use this.
Yeah, the foremen love it. It's the people who count the dollars and cents and say, why is it taking so long, that get upset.
Only if they're not getting paid for it. That's
right.
what I think. The specification itself, and really forward thinking. We've been talking about what we call performance pavement foundations, which is how do you set continuous pay scales for quality, not just for the pavement itself, but the pavement foundation. And that's another tool that I think will help implementation of it. It's do whatever you want, but this is what the state expects in terms of the support conditions. You can have freedom to figure that out. This is the tool we're going to use to verify it. So I think there's some creative things like that also that contractors are saying this looks pretty interesting. We'll have a little bit more control over how we're doing this. We just got to deliver the results. Great comments, and this is like a whole nother presentation just on the specification, the contracting. How do you implement this? Thank you.
Yeah, we have a couple more more questions and some on the chat. So I think I saw Supriya already hand, and then Chontao Dai. So Supriya, if you want to go and ask your question.
Sure. Thanks, Dr. White, for the presentation. It's really nice. So it's like everybody wants to go forward with this technology because it promises so much. And what you said about specifying what we want is the most critical thing here, because this K value that we talk about, 150 that we want, and then people, I think there is a need for all of us to understand that 150 on top of, let's say we are paving concrete or asphalt, and then we are looking at 150 of foundation layer. That's a composite value for the entire 3 feet of material. So instead of looking at just the top, I think everybody needs to look at 3 feet below it. And then do we need like 2 times of mapping? Like just before, I think most of the DOTs have some kind of base, sub-base materials in on top of subgrade existing material, especially in Midwest. We have clayey materials, silty clay materials. Obviously, silty materials, we will take it out. But that will not give us, and it always show us red when we go on this kind of existing subgrade. So addressing those kind of things as an expert in this field and educating the rest of us would be a great thing, because of the limitation of the technology in low K value range, let's say less than 50, or 50 is the K that typically, like the other questions that were asked before me, he was saying like contractor does what he needs to do in building that subgrade. He builds the subgrade based on what we tell them. Hey, I get 4 blows, I'm good with it, and you can build on top of it. You can put base, sub-base layers on it. But then he fails it after doing that because he's not getting 150. Because that's not the requirement for him. So please educate us. What is the status of the technology right now? Is it able to address the subgrade, existing subgrade issues, or the embankment that is being built per code, which is like 1 ton requirement in terms of that? So yeah, some light on this would be greatly appreciated.
Yeah, great. Thanks, Surprise. Surprise knows a lot about this stuff too. So 35 PCI is about the lower limit. Each layer of those 3 feet needs to have its own target value. So at the subgrade level, we might have a target value, say of 80 PCI, and then the next layer, it might be 110 PCI, and then the final composite would be 150. And again, that comes from design. So what's different about this is working with the design folks and saying, okay, we're going to build this to meet those requirements. What do you want? What do you want at the subgrade level? What do you want at the subbase level? What do you want for the composite value? Now let's translate those, put those in the machine. So during compaction of each layer, you know what you've got. I mean, the big thing about the foundations, if you don't get that underlying layer correct, it's going to be really hard on the contractor to get the results on the subsequent layers. So it absolutely makes sense to start, 3 feet's the minimum. Start there, make sure that's adequate. And if you have good results there, as long as you've got good materials, things tend to check out as you build up.
Good. So I think Dai also raised his hand, and then I'll go to questions from the chat. So Dai, please ask your question.
Thank you, Dave. Very good presentation. As you know, the ME design, typically people just put this 1 single modules for the base subgrade for the ME design. But in the laboratory testing part, and you get stress dependent behavior, like follow the testing protocols, right? So there's often difference between the laboratory testing modules with the field compared with the field modules measurements. So in your case, what would you recommend which modules to pick from laboratory testing for the pavement design?
Yeah, I think accounting for stress dependency is really important. That's the way forward. With the clay materials, modules tends to go down and stress increases, and then that's the opposite for the granite materials. The lab testing, we're very cautious now about using the lab test results, because what we see in the field when we do these in situ resilient modulus tests is that the composite behavior of a layered system and the boundary conditions are radically different than a uniform sample in the lab. We still do some lab testing periodically just as checks, but we're relying more on what we're seeing in the field now when it comes to stress dependent testing. So that may not be the answer you're looking for, but I think for us the future is resilient modulus measurement from what we're actually building in the field as opposed to the lab testing.
Yeah, I agree. But in the design phase, we do not know the modules at that time.
Yeah, that's the emphasis on, sort of rethinking pavement foundation design. I know from a design standpoint, you've got to make those assumptions ahead of time. Wouldn't it be great if we had more reliable data on the foundation materials that you work with in your state, so that when it comes time to construction, you have confidence those materials are going to meet those design modulus values. So this would be yet another presentation, as we figured out how to bring the field into the lab.
Yeah.
Instead of small samples, they're 3-foot diameter samples, and sort of going through and building up a catalog now of the actual results for materials in a given state, so that we've got this database to work from. And so far, the pavement designers are saying, well, this is great because now I've got something to base my assumption on, and that's going to help make decisions on, thicknesses of the materials, source of the materials, whether or not to use chemical or mechanical stabilization. And I've got this database now that I can confidently say this is what we're going to get when it comes time to field verification. So that's sort of a missing component of state of the practice right now.
Thank you, Dave.
Thanks for the question.
So a few more here in the chat. We have the first one from Yoab Sagaya. He asks, "It's finding the proper balance between increasing the number of the compaction passes to bring up the stiffness of weak sections, the red ones, and maintaining uniformity without over compacting the blue sections a challenge?"
Yeah, it's finding that balance a challenge. It's very much a focus point. I think Kurt was talking about the time aspect. If we are achieving the modulus that we want, get off those areas, then move on to the areas that aren't achieving those. So, I was talking to this foreman up in Pennsylvania last week, and he said, okay, this is Sierra. You're going to train her how to drive the operator. I told her 2 things. One is get in the machine and don't stop till the end of the day. And the second is don't get closer than 50 feet of me. And, as we talked, I said, I get it. You want a person in the compactor and they're just going to go all day. Now I said, here's a map. Would that change your perspective if we showed you that these areas are done and Sierra can stop and she can move to this area, which doesn't have that compaction yet? And that's when the light bulb, sort of clicked off. It was like, oh, you're allowing the operator to see the result of their work. And instead of just going back and forth all day, we're going to be smarter. We're going to be more efficient. We're going to dial this into the areas that we need it. So that's really the goal, is to get to that point where we move away from method specifications, 1 pass per inch of lift thickness, to achieve the requirements and then get off those areas. On the issue of overcompaction, that's a very real thing, by the way, on these granular subbases. It's a little dependent on the gradation, but 2 weeks ago, I was talking to an operator and I said, hey, we were at our 80% target and I just kept rolling for the next hour and it dropped down to 74%. What's going on? Well, it's over compaction. You know, achieve that value. If it goes down, you're just dilating the material. Now you're having to recompact it or you're degrading it. So making that data available to them, to me, is just a game changer in process control. Anyway, I hope that answers your question. I'm probably rambling a little bit too much there.
So I got a few more here. So Raul asked a question. Raul asked about the I-494 project, and if you actively communicated with team to address poorly compacted regions, and actually team Klein addressed that question in the chat, and he said that yes, you guys share information actively to address those poorly compacted areas, and the contractor spent some more time working the grade before paving last week.
Fantastic.
Yeah. Then
Great
we
work.
also have a question from Raul too. Another one. He says, "Can we import your modulus data into beta?"
I don't know about beta. I'm just not a user. But the data, importing data is probably a format issue. So we don't have any initiatives by any of the partners we're working with to format the data for that application. But formatting is just a transformation of data. So I don't see any reason it couldn't be. We just haven't been asked to do it.
Okay, perfect. Then I have Brett Dean. Is a copy of the spec available?
Yeah, we could provide that. It might be posted online. Kara, you would probably be the person to reach out to on that one. There's probably a few different versions of it. So you might want to talk to Kara. I'm sure she'd be happy to walk you through that.
Yeah, we have a different version depending on the type of project. So if you want to just reach out to me, send me an email. My information's in this slide deck, and then I can get you a link to the spec. It's on the DOT website.
Perfect. And I think that's the questions we have so far. So thank you very much, David and Kara, for your presentation. Just a reminder, next month, October 17, we have Bill Lykos from University of Wisconsin-Madison presenting on qualitative rating system for drainability of road-based materials. So we hope to see you there next month. Thank you so much.
Thank you. Appreciate the opportunity.
Thank you.
Thank you.